I welcome you all on this course on power plant engineering, and today we will discuss nuclear power plants. Topics to be covered in this lecture are pressurized water reactor, we will discuss pressurized water reactors, boiling water reactors, BWR, they are popularly called BWR, Canadian deuterium uranium, this is a Candu type of reactor, gas cooled reactor, liquid metal cooled reactor, and breeder reactors. In short, I have already introduced you these reactors in my previous lecture, but now we will discuss them in details. We will start with the pressurized water reactor. It is simple, light water cooled. Light water cooled means H2O. There is a light water and heavy water. So, this is a light water cooled reactor. It is a very unusual core design. This core design of this reactor facilitates forced and natural both type of cooling of the core, forced and natural. It facilitates both types of cooling and natural fuel and enriched fuel. So, it is a very versatile type of reactor. It is a pressure vessel. It has a thermal shield also, fuel element, reactor pressurizer. This is a unique thing here, pressurizer. Pressure is primarily very high. I mean, in this reactor, and the pressurize up to 100 bar. The primary circuit is pressurized up to 100 bar. If you draw this reactor, suppose this is reactor core. There is a heat exchanger. This we have done in the previous lecture also. Then after the heat exchanger, there is turbine, condenser, and then pump, and this is how the water is circulated, and this is the primary circuit, this is heat exchanger. And a pressurizer is provided here. So, pressurized, sometimes it is electrically heated to maintain the high pressure in the reactor, so that steam does not form, right. And this turbine is connected, this turbine shaft is connected to a generator to develop the power. This is feed pump, this is condenser, this is turbine. Okay. So, there are two circuits, primary circuits and secondary circuit, as I explained earlier, and this is, and the generation of steam takes place in heat exchanger, and this steam runs the steam turbine. So, there are certain advantages of these reactors. Now, advantage is the water is used as coolant, moderator, and reflector. All three functions are carried out by the water, and the water is cheap, easily available. So, this is a cost, I mean, this reduces the cost of the reactor. Power density is high. For this, density is high for this type of reactor. And fission products, they remain contained in the reactor, they are not circulated in the pipe, because they are solid fuel is used. So, they remain contained in the reactor, and small number of control rods, small, very small number of control rods are required in this type of reactor if you compare with the other reactor. Easy for inspection, you can easily go inside and inspect the turbine because it is a non-radiation area. So, and per kg of fuel extraction energy is high. Power, as I said, power density is high, that is also high, but per kg of fuel extraction of energy is also high in this type of reactors. It means less amount of fuel will be required for the same power generation if you compare with the other reactors. Now, there are certain disadvantages also. Capital cost is high. Capital cost high, because if you remember in the primary circuit we have to maintain temperature around 100 bar. So, all the components are designed so that they can bear their operation pressure is remaining 100 bar, for the operation pressure of 100 bar. Now, secondary, it is using secondary circuit. So, steam, it has to, this is primary circuit, there is a secondary circuit. So, for the the effective heat transfer, at least there has to be a temperature difference of 10 degrees centigrade. More temperature difference is better, but at least it has to be around 8 to 10, approximately 10 degrees centigrade. So, definitely this affects the efficiency of the cycle on the other side, right. So, that efficiency is comparatively low. There are, because water is being used as a moderator and as a coolant or as a shielding material, as a reflector, not shielding material, as a reflector, the corrosion problem is there. So, corrosion problem has to be dealt with in such type of reactor. And the third one, and the next one, which is quite serious, is that when we want to change the fuel channels, right, the reactor has to be completely shut down. So, it takes a gap of 1 or 2 months time. So, whenever there is a replacement of the fuel or the channel has to have to be replaced, the reactor has to be shut down for 1 or 2 months time. The fuel in the reactor suffers the radiation damage. Because it is confined to the reactor core. Insertion of control rod is also difficult. This is such a compact design of this reactor that insertion of fuel rod is also difficult in this reactor. And the fuel element fabrication of fuel element, it is also difficult in such type of reactor. So, there are certain limitations, or we can say disadvantage of pressurized water, this type of reactor. So, this is, we are done with the pressurized water reactor, right. The next is boiling water reactor. Now, the boiling water reactor, as it is clear from the name itself, the water boils in the core, right, and this water is directly used for running the turbine. There is no heat exchanger. The efficiency is certainly better than the pressurized water reactor. So, this simple arrangement, it is very simple arrangement. And enriched fuel is used. In this type of reactor. Natural circulation is possible, boiling water reactor, natural circulation is possible. And here in the boiling water reactor, the pressure has to be maintained constant. Pressure has to remain constant. Suppose there is a part load, there is a sudden decrease in the load. In that case, steam bypassing is done. So, when we are bypassing the steam, the same amount of fuel is used, but the less power is generated. So, if we look at the arrangement of this boiling water reactor, this is a pump here, which is used for forced circulation. It can be a natural circulation also. It directly goes, some valves, we can show some valves, and here there is a turbine connected to generator, and here there is a condenser which is used for taking away the heat, and there is a feed pump. Right. Now, there is a certain decrease in requirement of the power. We need less power. So, but the reactor core continue to generate the same amount of steam, and steam is bypassed. Steam is bypassed and it goes to the condenser directly, bypassing the turbine. Bypassing the turbine. Bypassing the turbine. Right? In that case, the efficiency is reduced drastically. So, if you look at the advantages of boiling water reactor, advantages. Now, first of all, there is no heat exchanger. No heat exchanger. So, when there is no heat exchanger, definitely it helps in gaining the efficiency. So, efficiency improves. Lower pressure vessel. Here we do not have to maintain very high pressure of the order of 100 bar. So, lower pressure vessel. With the lower pressure vessel, definitely there is a cost cutting in the material which is used for the fabrication of the reactor. Output temperature of steam is high. Because inlet temperature is high, so definitely output temperature is also be high, relatively high. So, it is efficiency of this boiling water reactor is greater than the efficiency of pressurized water reactor, right. But there are certain disadvantages also. First of all, disadvantages. First of all, contamination of turbines. Because the coolant, it goes to the core and then from the core it directly enters to the turbine. There is no heat exchange. So, this water which enters the turbines, it contaminates the turbine. So, if there is any failure of the fuel element, so the fission material will also enter the turbine. That is a dangerous situation, right. So, this is the major disadvantage. So, more precautions are needed in case of the boiling water reactor. And as I said earlier, there is a wastage of steam at part load. Right. And its power density is also limited because in a boiling water reactor, when the water enters from this side and leaves from the other side, only 3 to 5% of mass is converted into steam. Right. So, that is also a limitation of the boiling water reactor. And another thing is the possibility of burnout. Possibility of the burnout is more in the case of this reactor because the coolant is in directly contact with the fuel rod. Now, what is burnout? Now, if you take any pool of water, right, and keep on increasing the temperature. When you keep on increasing the temperature, the heat flux will also increase because heat flux is directly proportional to temperature difference, right. It will keep on increasing, it will reach a certain value. So, initially the nucleate boiling will take place and when there is an intense heating, in that case on the surface will start covering with a thin vapor film, right. So, the fuel will no longer remain in contact with the surface. In this situation because the same amount of heat has to be transmitted, the delta T shoots exorbitantly because the heat transfer coefficient reduces drastically and Q is equal to H delta T. So, when Q is same because the constant heat flux due to formation of film, thin film of the vapor, I am just telling in a nutshell. Okay. So, the H goes down drastically, this increases delta T and delta T may increase up to such an extent that the surface may burn out. That is, it is also known as, this flux is known as critical heat flux. But burnout means physically the surface physically burns out, and in this scenario if this happens in this boiling water reactor, the fuel will come out and it will get mixed with the coolant, and this will lead to a very dangerous situation. Okay. Now, the next type of reactor we are going to discuss is Canadian, deuterium, uranium reactor. This is known as Candu type of reactor, Canadian, deuterium, uranium, Candu type of reactor. And in India, many of the reactors which we have in India, they are modification of Candu type of reactor, and they are known as pressurized heavy water reactor or Indian pressurized heavy water reactor. Now, in this reactor, the heavy water is used as coolant. Heavy water, that is D2O, with a concentration of 98%. With a concentration of 98% natural uranium as a fuel with 0.235. So, this type of reactor is useful for the country which do not produce enriched uranium. Enriching uranium is also, I mean, is a costly exercise if you artificially if you want to enrich uranium. So, those countries which do not have the facility or which do not do the enriching of the uranium, right, this type of reactor are suitable for those countries. It differs from light water reactor. There are number of light water reactors. In light water reactors, the water H2O works as a coolant. Here it differs from light water reactor in that manner only, and here the heavy water used as a coolant. But the beauty here in this reactor is that only coolant has to be pressurized, not the entire reactor. Only coolant has to be pressurized. So, in case of any accident, in case of LOCA, the severity of the damage is very less, right. If you look at the arrangement of a typical Candu type of reactor, so there is a horizontal shell. In shell, there are number of channels, maybe 300, 400, 200 depending upon the design of the reactor. So, there are number of channels, right, and each channel, suppose I take one channel, each channel has a zirconium tube of, let us say, it depends upon the power generation, but normally the thickness is of the order of 1 millimeter or 1.2 millimeter zirconium tube, and concentrically a zircaloy tube is also used. This is zircaloy tube of thickness around 4 mm, close to the 4 mm, it depends. I mean, grossly it is 4 mm, and this tube has number of pins, fuel pins. Fuel pins are nothing but the zirconium tubes of approximately half inch diameter, and the uranium fuel pellets are filled in this zirconium tube, right. And each tube is known as fuel pin, and there can be a number of fuel pins in a grid, right, maybe 20, 30, 40 or 50 pins in a grid. Now, in a void space between these pins, the heavy water flows, that is D2O, which flows in the void space between these pins, and because the fission is taking place, the fission heat which is generated in these pins is transmitted to the heavy water, and part of the water is converted into the steam. Now, this steam which is generated is collected in a header. There is a steam header. In the top part the steam is, and from the top the steam is taken, and there is a heat exchanger again, and through heat exchanger the heat is transmitted to the working this fluid, that is H2O water, and again it goes to the turbine and condenser and then pump and again back to the heat exchanger, right. So, the beauty of this Candu type of reactor is the pressure, high pressure is there, but high pressure is there only in this pressure tube, inside the pressure tube, right, and this part is covered, is filled with the inert gas in order to prevent the heat transfer, and the entire assembly, there can be a, let us say 300 channels. So, 300 channels, assembly of 300 channels is placed in a vessel which is known as Calendria vessel. Now, the advantages of this type of power plant, first of all, enriched fuel is not required. First of all, enriched fuel is not required, natural uranium can work. So, and D2O is used as a moderator, and only D2O is pressurized, which is used as a moderator. So, sorry, D2 is also used as a moderator, not only as a coolant, it is also used as a moderator. So, when as a D2 is used as a moderator, it is multiplication factor is high. D2O has high multiplication factor, and which results in low fuel consumption. Right. And this Calendria vessel, the Calendria vessel where the tubes are fixed, it does not work on very high pressure, it works on the normal pressure. So, that material cost is also saved. Second thing is the ambient temperature is maintained between 65 to 75 degrees centigrade, between this range, right. And this, because this vessel is also filled with the water. So, it also acts as a, I mean, it also serves as a purpose of the safety also in this case, because we have several number of safety barriers. First of all, fuel pin is filled with the fuel, and it is filled in the pin which has also certain thickness. Then there is a pressure tube, then surrounded by the Calendria tube. Calendria tube is surrounded by the pressure tube, Calendria tube, and Calendria vessel. So, level of the safety is more in case of Candu type of reactor. Less time is needed for construction. Okay, and I said earlier, the moderator which can be kept at as a 65 to 70 degrees centigrade in this range, right. So, we can extract more work out of the or we can. So, moderator can be kept, and another point is moderator can be kept between the temperature of 65 to 75 degrees centigrade, which increases its effectiveness. It increases effectiveness and it slows down the neutron. The neutrons are also slowed down. Now, there are certain disadvantages also. Now, very high standard of design, manufacturing and maintenance. These things of very high state of the art design is required for Candu type of reactor. State of the art manufacturing is required, because several joints like roller joints are also have to be provided at the ends of the channel, and high level of maintenance is required in the Candu type of reactor. The coolant and the moderator are D2O, which is also itself is costly if you compare the cost with the light water. There are certain leakage problems are also there in the Candu type of reactor, and it has low power density. If you compare the power density of Candu type reactor, so it has low power density if you compare with the pressurized water reactor and boiling water reactor. So, for the generation of the same power, more space is required by the Candu type of reactor. The next is gas cooled reactor. Now, in the gas cooled reactor, all the reactors have, if you draw the schematic, all the reactors have this type of schematic. Now, this most of the reactor have this type of schematic. Now, here condenser, pump. Now, here the gas is used. Instead of liquid, gas is used as a coolant. So, air can be used as a coolant, hydrogen, helium, carbon dioxide, they can be used as a coolant. Here the moderator is graphite. In these type of reactor, the moderator is graphite, but the benefit is the problem of corrosion which persists in the case of where the water is used. Here, because air or the gases are used, the corrosion problem is not there. This problem is not there. If accident happens, they are relatively safe. So the level of safety is high. Thickness of reactor shield is much reduced. There are two types of gas cooled reactors. The one is gas cooled graphite moderator reactor, graphite cooled, gas cooled graphite moderator reactor. And another is high temperature gas cooled reactor, high temperature gas cooled reactors. So, GCGM and HTGC. So, there are two types of reactor, gas cooled graphite moderator reactor and high temperature gas cooled reactor. Both type of reactors has graphite as moderator. But this reactor uses natural uranium and this uses enriched uranium. That is the difference. So, this natural uranium is used in gas cooled graphite reactor, enriched uranium is used in high temperature gas cooled reactor. The pressure is 50 to 30 bars and the temperature goes to 700 to 800 degrees centigrade. Right. Now, advantages of gas cooled reactors. Gas cooled reactors advantage. Now, the advantage is the processing of fuel is simple. Process of fuel is simple. As I stated earlier, there is no problem of the corrosion in such of reactor and graphite remains stable under high temperature. It does not disintegrate. And if we are using CO2, it eliminates any possibility of the explosion in the reactor also, right. And this uranium carbide and graphite, they are able to resist high temperature. So, so these type of reactors can be operated on high temperatures. Now, there are certain disadvantages also. Fuel loading. Now, fuel, because here we are using gas, the density of gas is lower than the solids normally. So, the fuel loading is elaborate and costly. Right. Power density is low. Power density is low, right, because critical mass is high for this reactor, So, high mass has to be loaded initially because critical mass is high. If critical mass is low, initially low mass is required, but because here the critical mass is high, high mass is required is high mass of the fuel loading is required initially. And the another thing is if we are using helium, so helium diffusivity is high for the helium. So, there are leakage problems if you are using helium. Coolant is gas. So, more power, more bulk of the volume has to be handled by the pump. So, more power has to be consumed by the pump in this type of reactors, and control in coolant is also complicated, and because the negative coefficient of helium and it does not absorb the neutrons. And gas cooled, next is liquid metal cooled reactors. In previous lectures also I have drawn the schematic of the liquid cool where there are two heat exchangers. Right. So, in these liquid metal type of reactors, sodium is used at 7 bar. Sodium boils around 800 degrees centigrade temperature. So, the very high temperature can be maintained in such type of reactor. So, sodium can be pressurized up to or without pressure also, even if we do not pressurize sodium, in that case also this reactor can work efficiently. Thermal efficiency is high. Definitely if a reactor is operating on a high temperature difference in source and sink is high. So, thermal efficiency is going to be high. And graphite moderator is used. Graphite moderator, even low cost graphite moderator can be used in such type of reactor, and is smaller in size. They are smaller in size, and superheating is possible in such type of reactor because they are operating very high temperature. But the disadvantage is the sodium react very violently with water. So, in any case, in the remotest of the possibility, the mixing of sodium and water has to be avoided. Otherwise, a very violent reaction will take place. Thermal stresses, because it operating very high temperature, thermal stress is also an issue in these type of reactor, and the heat exchanger in this type of reactors have to be leak proof. Because if there is a leakage, again there will be reaction of sodium with the moisture with the atmosphere or with the liquid which is circulated in the secondary circuit. So, that is why shielding of first and second stage is done, right. So, the major disadvantages of this reactor is the leakage of sodium is very dangerous. Now, the next one is the breeder reactor. Now, it is clear from the name itself, the breeder reactor can also be used for generating fuel. In a breeder reactor, the mass of the fuel or the fuel which is consumed and the end product is more fuel is generated, and at the same time power is also generated. So, it is used for the breeding or the generating the fuel, and breeder reactor is also used for the power generation. So, it has a small vessel and some amount of enriched plutonium is kept with moderator. Enrich, and there is a fissionable material which absorbs the neutrons surrounding the vessel, The core is cooled by liquid metal. So, liquid metal is and additional, because here the gamma radiations are also there. So, additional shielding is a very robust shielding is provided surrounding the reactor. When uranium 235 is fissioned, enormous heat is liberated, and at the same time neutrons also are also liberated. If U-38 is kept in the vicinity or a part of the reactor, after the reaction it can produce. So, after reaction with 235, this uranium 238 can be converted into the fissionable material. This is how the fast breeder reactor works. So, it consumes the fissionable material, and end product is more fissionable material, and at the same time heat is also liberated which can be used for the power generation. That is all for today. Thank you very much.